name is Yukari Katsura. I work at the National Institute for Materials Science, the University of Tsukuba and Riken. Together with many collaborators, I lead the Starrydata project. In this video, I will explain three things: how Starrydata collects experimental data from the literature, how it supports data-driven analysis, and how it connects to several papers in STAM and STAM methods. Every year, thousands of papers are published in each field of materials science. In each paper, there are plot images containing experimental material property. However, most of such data are not reusable from data science. So we wanted to collect experimental data from many more papers to view it as one large galaxy. This is why we started our project Starrydata. It is designed as a community-based literature database. We are trying to turn published plot images into a large digital dataset that can be used for materials informatics. In Starrydata, we are trying not to violate the copyright of the publishers. When we find plots of materials property data, we extract the numerical values and the metadata such as composition, measurement conditions, and experimental methods. These numbers are scientific facts. They are not the creative expressions that copyright protects. We also always keep clear links back to the original papers. In this way, we can share and analyze the data together. This process may look like a lot of manual work. Many people think, why don't you just use image recognition and fully automate it? For more than 10 years, many groups have tried that approach. Our experience is different. In Starrydata, we always keep human curators in the loop. They read the papers and choose important figures. Then they select suitable tools for each plot. One main tool is our web-based Starry digitizer, which also has semi-automatic functions. After that, the curators check the output and register the data in the database. In the future, the AIs will become stronger, and the publishers may allow us more automatic processing of figures. Then, our data creation experience will help teaching AIs to do the job. Since 2016, our team and collaborators have used this workflow for many kinds of materials. For thermoelectric materials, we have data from thousands of papers and tens of thousands of samples. We also make datasets for magnetic materials, other condensed matter systems such as quartz crystals and battery materials. All these datasets are available through our web system Starrydata 2. The whole dataset is open, so it can be downloaded freely and can be used by citing our paper. After registration, you may join the data creation and create your own list of papers. When we digitize many figures, we can make all data plots. In these plots, we put together thousands of data curves from many papers. For thermoelectrics, for example, we can show Seebeck coefficient, electrical resistivity, thermal conductivity, and the dimensionless figure of meritocity. We can include many materials families in one view. With this view, we do not see only a few record-breaking points. We also see the wide distribution of ordinary samples. We can see how different materials stay in different regions of property space. Starrydata 2 also has interactive tools. We provide 2D scatter plots, 3D scatter plots, and PCA-based visualizers. Users can filter by composition, temperature, or property range. This three-dimensional scatter plot shows ZT values as color. The axes are the Seebeck coefficient, the logarithm of electrical conductivity and thermal conductivity. We can observe a universal trend, including the region of optimal thermoelectric properties for high ZT. We have published 6 papers in STAM and STAM methods related to Starrydata. I will briefly introduce each of them. This was our first paper reporting the Starrydata project. We collected curve data for over 400 samples of lead telluride type thermoelectric materials and estimated electron relaxation times by combining the dataset with Boltzmann transport calculations. This paper has been cited by many researchers who use starry data sets in their own work. In this paper, we examined how bias in experimental datasets affects machine learning models. Because our dataset is heavily concentrated on well-studied thermoelectric materials, we discussed how to define the applicability domain in chemical space for machine learning. This is a review of our collaborative research project with experimentalists. We used our materials informatics tools, including Starrydata, to discover new inorganic materials. We constructed a large dataset of dielectric properties in collaboration with industry. Our team collected the data and the engineers in industry carried out the analysis and machine learning. This dataset will be released soon as an open dataset when the 1-year embargo expires. This paper describes the Starrydata 2-web system as a whole. It covers the system architecture and explains how we handle paper selection, data extraction, data sharing, and data visualization. Our latest work focuses on applying large language models, or LLMs, to create data more efficiently. In the Starrydata 2-web system, we added an auto-suggestion function. We send the experimental methods section of an open access paper to an external LLMs through an API, and it proposes candidate sample information. Creators then check and confirm this information. We also built a custom GPT called Auto Summary GPT. It converts PDFs of open access papers into structured summaries of figures, tables, and samples. This gives us a well-organized starting point for more detailed curation. In summary, Starrydata is our attempt to convert published figure images into a shared machine-readable dataset like a starry sky of materials data. We want to expand this digitization to many other fields of materials science. We hope that many more researchers will join this data creation and use our datasets to understand and apply machine learning to the overall structure of their research fields. Once we succeed, materials informatics will be more deeply connected with experimental materials science, and we believe that researchers will discover better materials more efficiently. Thank you for watching.